So thank you for joining this lesson. We're going to study number 17 in this paper, whereby we are told to study figure 8 and answer the following questions. So the figure 8 is here. We can see a radium source. So the radium source is a radioactive substance. It releases the radioactive particles or the several types of radiations which are expected from a radioactive substance. We have a plate X and another one Y. Then of the radiations which have been emitted from this radioactive substance, we can see a radiation A, we can also see a radiation B, and we can also see another radiation here which has not been named. Let me call it C. Just have it as C. State the charge on plate X. State the charge on plate X. So for us to identify the charge on plate X, there are a few things we're supposed to know. One, we can see there is a radiation which has been attracted, or rather which is deviating towards plate X. Then according to the type of this radiation which is deviating towards X, we can see the deviation is so big, which means that radiation A is very light. It is an emission of very light particles, and these light particles I expect to be electrons which are negatively charged, and they are called beta particles. So because we can see the plate X is attracting electrons which are beta particles, a conclusion that they are beta particles is due to the bigger deflection due to their small mass. So we can say because of the bigger deflection, then these are electrons or other beta particles. And now that the beta particles are negatively charged, we can say that plate X is positively charged. So it is positive charge. We have a positive charge on the plate X. A continuation. On the other side, we are taught to identify radiations A and B. So for us to identify radiations A and B, we have already said A is beta particles. So A is going to be beta particles, or rather beta radiation. It's emission of beta particles. And B, we can see it is passing through the electric field undeviated. It is not affected by the field. It is neither attracted to X or to Y. So B is going to be gamma radiations which have no charge. These are gamma radiations. They are the ones. So we say gamma here. Reason being that it is just a type of energy which is not having any charge, so it cannot be affected by the field. Part 2, we are told a nuclear reaction is represented by the following equation. So you have a substance X having a mass number A and an atomic number 192. This is 92, sorry. So we have 92 and A. Then after undergoing a radiation, or rather a nuclear reaction, it releases alpha particles and it becomes Y with 234 as the mass number and an atomic number of B. Then we are taught to determine the values of A and B. So for us to know the values of A and B, we should understand that the release of an alpha particle is the release of what we call an helium particle, which has a mass number of 4, atomic number of 2. That means the substance which is losing the alpha particle will have its mass number reducing by 4 and the atomic number reducing by 2. Therefore, it was 92, the atomic number, and it is now B, so that we may have an alpha particle released. In simpler terms, we can say X is having A and 92. So it is going to become wire, which is having 234 and B plus an helium particle. So we're going to say that on both sides, the atomic number has to be equal. Therefore, we shall have 234 plus 4, which is 238. So it means on the other side where we have A, it is also going to be 238 because the atomic number decreases by 4. That is why it becomes 234 after losing 4. So it was 238. Then B, we have 90 already and it loses 2. So it means it becomes 90. So the new atomic number is 90. So that is how the reaction is to be solved. Part 4. A radioactive source has an activity of 810 counts per second, and after 63 hours, the count rate falls to 110 counts per second. If the background count is 10 counts per second, determine the half-life of the source. Therefore, what we're going to do here, we're going to say there is a initial count. We call it N0. The initial count is 810, but now we are having a background radiation. So the background radiation means even when a radioactive source is not around, the counter is already recording 10 counts per second, which means now the real initial count is going to be 800 counts per second. Now that we have reduced or subtracted the background count, then we also say now the remaining number is exactly 100 counts per second, because in the 110 counts per second, we have 10 counts being the background count. Therefore, now we can say this is happening after a time of 63. After a time of 63. So we usually say the remaining number is usually given by the initial number multiplied by half. Then half is raised to t, which is the time taken out of small letter t, which is the half-life. Therefore, we can get t over t by saying n, which is 100, divided by the initial 800. N equals to, we have 800 here, then half raised to the unknown t out of t. T out of t. The time taken divided by half-lives, or rather the number of half-lives. Therefore, we're going to have now 100 over 800 equals to half raised to t out of t. So now with this, we can simplify and say 1 over 8. We say 1 over 8 equals to half raised to t out of t. So we can make this one in terms of half, whereby 1 over 8 becomes half power 3, which is equals to half raised to t over t. So which means the number of half-lives, which is t over t, is equal to 3. So in 63 hours, we have 3 half-lives. Therefore, we can get 1 half-life. Now we're going to say that 1 half-life is going to be 63 out of half-life. We get 3 half-lives. Therefore, to remain with t, now we go to divide 63 out of 3, and this will give us 21 hours. So the half-life in this case is 21 hours.